Good day and welcome back. This is our fourth installment investigating arc length, curvature, and more. And we're firmly in that more portion of the discussion. In the previous video, we introduced the idea of unit tangent, unit normal, unit binormal vectors, along with a few planes of interest relating to them, specifically the normal plane and an osculating plane. In this video, what I'd like to do is just take one example, this helix which wraps around the z-axis, and go through and compute these quantities of interest. So I'll warn you ahead of time, this is a highly computational example slash video. But the nice thing about these problems is even though they're highly computational, we do have this really methodical approach, just one incremental step at a time. So let's begin. Finding the unit tangent is kind of the old portion of the problem. We need to find r prime and its magnitude. So r prime is minus sine cosine 1. We differentiate component by component. The magnitude of r prime is the square root of sine squared plus cosine squared plus 1 squared. And I feel like we've seen similar things on multiple occasions now. Sine squared plus cosine squared is 1, so this is really the square root of 2. So the unit tangent vector is going to be r prime divided by its magnitude. So you don't need to write this down, but just to remind everyone, dividing by the magnitude is putting a 1 over root 2 out front, and r prime is minus sine cosine 1, which completes the first step of finding that unit tangent vector. And what I would request that you do, say for homework and exams, is as you find these quantities, simply put a box around them, make it as easy as possible for me to see them, and also organize your work in a nice vertical flow and include plenty of space so that if there is mistakes, I can go through and easily add comments. So continuing on, to find the unit normal, we now need t prime and its magnitude. So t prime, we have a constant multiplied by the derivative of the associated vector. So term by term, we would have minus cosine minus sine 0. And we also need the magnitude of t prime. And remember, if you have the magnitude of a constant times a vector, you would get the absolute value of that constant. And I'll add that in there. Note 1 over root 2 is positive. You do not need that absolute value. Times the length of the vector. So cosine squared plus sine squared. Cosine squared plus sine squared is 1. So the length of that unit tangent vector is 1 over the square root of 2. And that gives us the unit normal vector. The unit normal vector is t prime divided by its magnitude. And remember, you do not need to write down this step, say on a homework assignment, but just to make sure we are all on that same page. So t prime, if we just cut and paste from above, all divided by the magnitude of t prime, which is 1 over root 2. So 1 over root 2, 1 over root 2 cancels, and this gives us a nice convenient formula for the normal vector. It is the vector minus cosine minus sine 0. And once again, I would appreciate it if as you find these quantities, just go ahead and box them in. Make it as easy as possible for me to follow your work. Lastly, we're also asked to find the unit binormal vector. And remember the order that we have progressed. Unit tangent, then unit normal. That dictates to us the order for the binormal. It's t crossed with n. So we have this 3 by 3 determinant. So ijk across the top row. In the middle row, we have the vector t. And I'm just going to note that if you have a constant, you can go ahead and pull that constant in front of the determinant. So we could write 1 over root 2, that constant, and then minus sine cosine 1. And then we finish up with the normal vector, minus cosine minus sine 0. So we have the 1 over root 2 hanging around out front. The first entry for this binormal vector would be what? Cosine times 0 minus a minus sign. So positive sign. That second entry, there's going to be a negative sign, which is there because remember our pattern, plus, minus, plus. Then we'll have minus sign times 0, so 0 minus a minus cosine. And then for that k component, we will have sine squared minus a minus cosine squared. Sine squared plus cosine squared is 1. And this is our unit binormal vector. So as claimed ahead of time, highly computational, but at the same time, very methodical. You know right from the beginning exactly which steps you are going to follow to get from the unit tangent to normal to binormal vectors. Let's look at one more example. Now that we have these unit tangent, unit normal, unit binormal vectors, let's go ahead and determine the normal and oscillating planes. And note we're given the point of interest, 0, 1, pi over 2. So we know the point that we are dealing with on both of these planes, whose equation we will write down. So 0, 1, pi over 2. What we need to do in either case, whether it's finding the normal plane or the oscillating plane, is we need to determine the normal vector to the plane. So our observation at the end of the previous video is that the normal vector to the normal plane, and I realize there's a lot of normals going on here, so I apologize, but that's just part of the language and material, is the unit tangent vector corresponding to this point. And I'm going to scroll up just a little bit so that we can compare with our vector valued function representing the space curve. I want to know what value of t will put me at this point. And we can specifically focus in on that third component. The third component is t. So t is equal to pi over 2, which means that is where we would like to evaluate the unit tangent vector. So the vector orthogonal to the normal plane is going to be the unit tangent vector at pi over 2. And if we look above, we see that the unit tangent vector at pi over 2 is going to be 1 over the square root 2 times at pi over 2, we have minus sine of pi over 2, cosine pi over 2, and 1. So this would be the vector minus 1 over root 2, 0, 1 over root 2. So the normal plane is the vector passing through the point 0, 1, pi over 2 with normal vector given here. So if we put this together, we have the normal plane is determined by minus 1 over root 2, x minus 0, plus 0 times y minus 1, plus 1 over root 2, z minus pi over 2, and all of this is equal to 0. And I agree if you're thinking we don't need to write the middle term down and you don't need the x minus 0. I include all of this just because it seems like it's been a little while since we were doing equations of lines and planes, and I want to make sure we see where each of these quantities comes from and how they are combined. Lastly, we can do a very similar computation to find the oscillating plane. And what I'd recommend at this point is maybe hit pause, take a minute, and see if you can come up with the equation of that oscillating plane. Okay, so recall from the end of the previous video once again, the vector orthogonal or normal to that oscillating plane is determined by the binormal vector at that point P. So in this case, pi over 2. And if we substitute that in to the formula we see directly above, recall sine of pi over 2 is 1, cosine pi over 2 is 0. And if we distribute that 1 over root 2, we are going to have 1 over root 2, comma 0, comma 1 over root 2. So the equation of the oscillating plane at the point 0, 1 pi over 2 would be 1 over root 2 x minus 0 plus 0 times y minus 1 plus 1 over root 2 times z minus pi over 2, and this is all equal to 0. And this completes the discussion for the fourth video, and it really completes the material for the section as well. But as usual, a very important component of this learning process is to go through and practice examples. So as usual, if you have questions, feel free to reach out to me, drop me an email, stop by the virtual office hours. What remains in our fifth and final installment of this section will be a class worksheet. Typically during the semester, I would give you all probably a solid 25 plus minutes to work on the worksheet you can find posted in Canvas, and then I would go over portions of it in class. So go to that worksheet, see what you can complete, and stay tuned for more. Take care.